Hello, welcome back. In Module 1 and 2, we learned about the computational techniques on implementing the simplex method for solving linear programming problems. Notice that in the examples chosen in Module 1 and 2, all the constraints other than the non-negative constraints are of the type less than or equal to. So, it was easy for us to get the standard form of the given linear programming problem along with the introduction of the slack variables. But if the constraints are of type greater than or equal to, then by converting the constraints to equations, we will not get the standard form. Then we have to follow certain new techniques to get the standard form of the given linear programming problem, which we shall learn in this module. To know more about it, we shall consider a linear programming problem given by minimize z is equal to 4x plus y subject to the constraints 3x plus y is equal to 3, 4x plus 3y greater than or equal to 6, x plus 2y less than or equal to 4, x comma y greater than or equal to 0. Let us rewrite this problem as maximize z prime is equal to minus 4x minus y subject to the constraints 3x plus y is equal to 3, 4x plus 3y greater than or equal to 6, x plus 2y less than or equal to 4 and x comma y greater than or equal to 0. Here the minimization problem is converted into a maximization problem so that we can follow the same simplex algorithm that we have learned so far on this maximization problem and then obtain the solution for the given minimization problem by reverting the sign of the optimized objective value of this maximization problem. Now, representing all the constraints as equation, this maximization LPP is written as maximize z prime is equal to minus 4x minus y subject to the constraints 3x plus y is equal to 3, 4x plus 3y minus s1 is equal to 6, x plus 2y plus s2 is equal to 4, x, y, s1, s2 all greater than or equal to 0. For easy and quick reference, let us name the constraints 3x plus y is equal to 3 as C1, 4x plus 3y greater than or equal to 6 as C2 and x plus 2y less than or equal to 4 as C3. Here the constraint C1 representing 3x plus y is equal to 3 is an equation and hence is kept as it is. The second constraint C2 representing 4x plus 3y greater than or equal to 6, the left hand side 4x plus 3y is larger than the right hand side value 6. Hence, by removing S1 greater than or equal to 0 from 4x plus 3y, we get the equation 4x plus 3y minus s1 is equal to 6. In the third constraint C3 representing x plus 2y less than or equal to 4, the left hand side x plus 2y is smaller than the right hand side value 4. So, by adding s2 greater than or equal to 0 with x plus 2y, we get the equation x plus 2y plus s2 is equal to 4. Now, rearranging the same linear programming problem, we have maximize z prime is equal to minus 4x minus y plus 0 s1 plus 0 s2 subject to the constraints 3x plus 1y plus 0 s1 plus 0 s2 is equal to 3, 4x plus 3y minus 1 s1 plus 0 s2 is equal to 6, 1x plus 2y plus 0 s1 plus 1 s2 is equal to 4, where x, y, s1, s2 are all greater than or equal to 0. Since the problem has three constraint equation, it must have the basis 1 0 0, 0 1 0 and 0 0 1. Here s2 holds the basis 0 0 1 and the other two bases are missing. Hence, the given linear programming problem is not the standard form and hence the simplex method cannot be implemented to find the solution for the given linear programming problem. Hence, to solve by the simplex method, we can forcibly insert the two missing bases with the help of the variables say a1 and a2. That is, the modified problem is maximize z prime is equal to minus 4x minus y plus 0 s1 plus 0 s2 subject to the constraints 3x plus 1y plus 0 s1 plus 0 s2 plus 1a1 plus 0 a2 is equal to 3, 4x plus 3y minus 1 s1 plus 0 s2 plus 0 a1 plus 1 a2 is equal to 6, 1x plus 2y plus 0s1 plus 1s2 plus 0a1 plus 0a2 is equal to 4, where x, y, s1, s2, a1, a2 are all greater than or equal to 0. Since we have added two new variables for the sake of introducing the missing basis, this problem is different from the original maximization problem. Hence, to drift back to the original problem as and when we proceed through the simplex method iterations, a technique called Bigham technique is introduced. By this technique, introduce a negative of a huge number as coefficient of the variable a1 and a2 in the objective function. That is, by using Bigham technique, the problem becomes maximize z prime is equal to minus 4x minus y plus 0s1 plus 0s2 minus 1000 a1 minus 1000 a2, subject to the constraints 3x plus 1y plus 0s1 plus 0s2 plus 1a1 plus 0a2 is equal to 3, 4x plus 3y minus 1s1 plus 0s2 plus 0a1 plus 1a2 is equal to 6, 1x plus 2y plus 0s1 plus 1s2 plus 0a1 plus 0a2 is equal to 4, where x, y, s1, s2, a1, a2 are all greater than or equal to 0. Here we have the big M value as 1000 and introduced minus 1000 as the coefficients of a1 and a2 in the objective function. By Bigham, it means that the huge number chosen is relatively bigger than any given number in the problem and dominates in all computations. This form of the linear programming problem, which has all the bases 1 0 0, 0 1 0, 0 0 1, is the standard form of the given maximization linear programming problem. Hence, this problem can be solved by the simplex method. Since the variables a1, a2, s2 hold the bases 1 0 0, 0 1 0 and 0 0 1 respectively, they are the basic variables. To get the initial simplex table, set the non-basic variables x, y and s1 to 0. Hence, we get the initial simplex table. Since the most negative element of the NER corresponds to x column, x is the entering variable. Now, dividing the SOL elements by the corresponding elements of the x column, we get 1, 1.5 and 4. Hence, the minimum ratio is 1, which corresponds to a1 row. Therefore, the pivot element is 3. Applying the row transformations in order to shift the basis from the leaving variable column to the entering variable column, we get the second simplex table. In the second simplex table, the most negative of NER is under the y column. Hence, y is the entering variable. So, dividing the SOL elements of the corresponding entering variable column elements, we get 3, 1.2 and 1.8. Hence, the minimum ratio is 1.2, which corresponds to a2 row, and therefore, a2 is the leaving variable, and this gives the pivot element as 1.667. Applying the row transformations in order to shift the basis of the leaving variable to the entering variable, we get the third simplex table. In the third simplex table, the most negative of the NER is in the S1 column. Hence, S1 is the entering variable. Now, by dividing SOL elements by the corresponding entering variable column elements, we get 3 for the x variable row and 1 for the S2 variable row. The second ratio that corresponds to y variable row is not considered for the comparison, as the ratio is found by dividing with the negative number. Hence, the minimum ratio is only among 3 and 1, and that is 1, which corresponds to S2 row, and therefore, S2 is the leaving variable. This gives the pivot element as 1. Applying the row transformations in order to shift the basis of the leaving variable to the entering variable, we get the fourth simplex table. So, since all the values of the NER of the fourth simplex table are either positive or 0, this table is the optimum table. Hence, from this optimum table, we can find the solution for the maximization linear programming problem. That is, x is equal to 0.4, y is equal to 1.8, and maximum z prime is equal to minus 3.4. Therefore, the solution of the given minimization LPP is x is equal to 0.4, y is equal to 1.8, and minimized z is equal to 3.4. Thus, this Bigham technique helps us in overcoming the modifications provided in the original problem for obtaining the standard form and get the solution for the original problem. Now, let us learn about some more special cases in simplex method. For that, let us consider the linear programming problem. Maximize z is equal to 2x plus y subject to the constraints x minus y less than or equal to 10, 2x less than or equal to 40, x and y greater than or equal to 0. Writing this linear programming problem in the standard form, we get maximize z is equal to 2x plus y subject to the constraints 1x minus 1y plus 1s1 plus 0s2 is equal to 10, 2x plus 0y plus 0s1 plus 1s2 is equal to 40, and x, y, s1, s2 all are greater than or equal to 0. Since s1 and s2 are basic variables, setting the non-basic variables x and y to 0, we get an initial simplex table. Further continuing the iterations, we get the second and third simplex tables. In the third simplex table, the entering variable is s1. We always find the minimum ratio from the ratios found by dividing the solution column by the element of the corresponding entering variable column element only when the dividing element is strictly greater than 0. Notice that here both the dividing elements are not strictly greater than 0. Hence, it is not possible to find the ratios and hence to find the minimum ratio also. This situation in the simplex table is the indication that the solution is unbounded. To make it more clear about this phenomenon in the simplex table, let us consider the graphical representation of the constraints of this problem. Notice that in the graphical representation, the feasible region is not bounded in the x2 direction. So, it is possible to improve solutions repeatedly by changing the points in the feasible region. These solutions form an unbounded sequence of values, where each value is better than its previous. Hence, solutions of this type are said to be unbounded. So, whenever we encounter a situation in a simplex table where it is not possible to find the minimum ratio without attaining the optimum table status, it is an indication that the solution is unbounded. In order to have a better understanding, let us solve one more problem. Maximize z is equal to 20x1 plus 10x2 plus x3 subject to the constraints 3x1 minus 3x2 plus 5x3 less than or equal to 50, x1 plus x3 less than or equal to 30, x1 minus x2 plus 4x3 less than or equal to 20, where x1, x2 and x3 are all greater than or equal to 0. Writing this linear programming problem in the standard form, we get maximize z is equal to 20x1 plus 10x2 plus 1x3 subject to the constraints 3x1 minus 3x2 plus 5x3 plus 1s1 plus 0s2 plus 0s3 is equal to 50, x1 plus x3 plus 0s1 plus 1s2 plus 0s3 is equal to 30, and x1 minus x2 plus 4x3 plus 0s1 plus 0s2 plus 1s3 is equal to 20, where all the variables x1, x2, x3, s1, s2, s3 are all greater than or equal to 0. Since s1, s2 and s3 are basic variables, setting the non-basic variables x1, x2 and x3 to 0, we get the initial simplex table. By continuing the iterations, we get the second and third simplex tables. Note that the simplex table is not optimum, as there is one negative value in any year. This implies that s1 is the entering variable, but we cannot find the leaving variable as no ratio is eligible for finding the minimum ratio. Hence, this situation in simplex table indicates that the solution is an unbounded solution. Next, if there is no point that satisfies all the constraints, then there is no feasible region in the graphical representation of the given two variable problem. Here, we call the solution to the problem as an infeasible solution. Our next task is to study the conditions under which the simplex iterations lead to infeasibility. Let us take an example problem to illustrate this. So, maximize z is equal to 3x plus 2y subject to the constraints 2x plus y less than or equal to 2, 3x plus 4y less than or equal to 12, where x and y are greater than or equal to 0. Writing this linear programming problem in the standard form, we get maximize z is equal to 3x plus 2y plus 0s1 plus 0s2 minus 1000 a1, subject to the constraints 2x minus 1y plus 1s1 plus 0s2 plus 0a1 is equal to 2, 3x plus 4y plus 0s1 minus 1s2 plus 1a1 is equal to 40, where x, y, s1, s2 and a1 are all greater than or equal to 0. Since s1 and a1 are the basic variables, setting the non-basic variables x, y and s2 to 0, we get the initial simplex table. Continuing the iteration, the second simplex table is shown here. Notice that the second simplex table is optimum, but the artificial variable is still there in the basis. As the simplex iteration is designed to move along only the corner points of the feasible region, while moving from one corner point to another corner point, the straight line representing the objective function assumes the new corner point as one that belongs to the feasible region, but actually it is not. That is, actually the regions of the two constraints do not overlap. This implies that there is no feasible region for the given linear programming problem. That is, whenever the optimum is attained without artificials leaving the basis, it is the indication that the solution is infeasible. So, in this module we have learned about the Big M method and two more special cases that arise while solving the linear programming problem using the simplex method. The next module we shall study about the two-phase method, which is the alternate method for the Big M method. See you in the next module. Thank you.